We're going to start today by giving you a presentation about imaging large 2D surveys in an automated 3D environment for optimization of the parameters and the processing efficiency. Basically what it means, we're going to talk about tomography in a 2D sense, but also in a 3D sense to have the better velocity volume we can get for our dataset. As we know, 2D dataset is a very different challenge from dealing with 3D dataset. So for instance, one of the main challenge, is that the first one is that it's very labor intensive, i.e. it remains a lot of human interaction with your dataset. Also, obviously, it's very data management intensive, i.e. you need a lot of interaction as well with the different lines you're going to deal with. And sometimes you have hundreds of files for just one line, which can then be stored somewhere. So basically, it's very data management intensive and also, obviously, human intensive. Also, as we know, 2D datasets still represent a lot of acquisition still nowadays. About 25% of the acquisition in the world are around 25% are 2D seismic acquisition. Can you hear me well? Sorry, I'm just trying to... Yes? No? Not yet? I'll try to speak a bit better. Obviously, usually the case for 2D dataset is to first understand the geology of an area before some 3D datasets are acquired. So therefore, it's very important that we deal as well with those datasets before doing some 3D dataset. And obviously, the vast majority available still nowadays, historically speaking, is 3D dataset. So obviously, dealing with 3D dataset in the processing sense is still very much needed in our industry today. So the challenge is, as I was mentioning that before, as I'm going to show you later, all the tomography, all the migration we're doing is centered around our 3D visualization tool called 3D Canvas. Everything will be done within this canvas here. So i.e. on this 3D visualization tool, the good point is that you can QC your 2D lines very easily. You can also do multi-line interpretation in one go, because otherwise if I do one line, and one line, sometimes I'm not sure where actually this horizon finishes and where the other one starts. We can also do gather conditioning within 3D Canvas, which means, for instance, TOPI, or can be FK filter, NMO, and so on and so forth, and then restacking on the fly and displaying straight away on your visualization tool. You can also QC the autopic RMO curves, so i.e. after you've done some tomography, for instance, you want to follow those unflatness of the gathers. So you can do that straight away as well on the 3D canvas. You can also edit your RMO for the tomography. So we have some QC tools, which mean it's compass all the different RMO curves in one go. So I'm going to show you that later as well in the demonstration. And last but not least, it's also efficient QC for the tomography of the results. i.e. when you obtain your new velocity model, you can display it again and compare that to what you had before. So the agenda, what I'm going to show you today, is basically a velocity model, the whole workflow, because we're going to have a velocity model which is going to flatten our CRP gather, and also we are going to have the tie lines to each other, i.e. if I have some intersection of lines, I don't want to have missed ties that normally you will have if you do normal processing. So therefore, by doing this workflow, I will have not only a velocity model which is work well for each line, but also a true model in 3D sense. So i.e. all the lines will be tied to each other. So to do that, what I'm going to show you obviously is a workflow, the multi-line workflow including the missed tie, but also something new which has been released in Paradigm 19 called the parameter testing. i.e. just on the fly, I can test different parameters, and straight away, I'll be able to QC those different parameters on my 3D canvas. Bear in mind as well that the presentation I'm going to show you later is on the cloud. So i.e. everything you will see is just as easy as you would have done if you're logged on somewhere and doing as well with our software. Right, so this is the general workflow when you work with 2D dataset normally. So first of all, you have a first interval velocity model, and then you use this interval velocity model to run a first pre-stack depth migration. Then after that, you QC your CRP gathers, and most of the times they will not be flat yet. So i.e. you'll have either some events pointing toward the top, some events pointing toward the bottom. Your velocity model will not be yet ideal. So that means that we need to do a tomography in order to have a better velocity model, in order after that to have a better positioning of the events. So to do that, I don't know if you're all familiar with the equation of the tomography, but this is the general equation at the top there. We have delta t represent your time error on your CRP gather, i.e. the time difference between the flatness and what actually the event is, the real events. So that's my delta t here. The A matrix represents the information along the ray path that you have shot to have your information. And delta M represents the model updated minus your initial model. So it can be just the velocity model, or it can be your anisotropy model, and so on and so forth. And here, for instance, you just have a representation of where I shoot my rays in order to get all those information. So to shoot my rays, what do I need for my tomography? First of all, I need to know where I'm going to shoot my rays. I don't want to shoot my rays everywhere because some information are just noise. I don't want to shoot the rays from this noise. So to do that, we're going to compute two different attributes. We're going to compute the structural dip, and we're going to compute as well the continuity. The continuity will follow the continuity events of my data set. So i.e. everything which is not relevant will not be continued in my matrix there. Then after that, I'm going to put all those information into a unique database called a pencil. That's a vertical function used to store different information, different useful information for my tomography. Then I'm going to run the pre-stack auto picker, i.e. from those points, I'm going to shoot those rays, I'm going to find actually where those delta T are on those CRP gather. And then after that, I've got all those information needed to do my tomography. So first of all, I'm going to build the matrix, and then, so the A matrix you see here, and then I'm going to solve the matrix. And after that, I'm going to have a new model. And with this new model, what I'm going to do, I'm going to run a new pre-stack depth migration, and hopefully, my CRP gather will be much flatter. Maybe sometime you might need more iteration, but at the end, the goal is really to have a flattened gathers for the whole sections, basically. So after a couple of iterations, all your gathers should be flat. That's your 2D workflow here. But basically, because so far we have just worked on the 2D sense, so that means that sometime you may have some misties over the intersection of the lines. And that's a problem we need to face as well. So to do that, what we need to do is the velocity file we had there, we need to extrapolate that as a 3D sense to cover the fall of the survey. And then we need to convert the pickings of the horizon as a 3D grid as well. And then we need to compute some misties. So I, from those pickings of the horizon, I have some misties there. I need to create those misties in order to put that here in the map mistrie. Then all those information I put in our 3D pencil. So I mentioned the 2D pencil before. Similar things in a 3D sense, obviously, here. And then I can build something called a time-preserving tomography. Time-preserving tomography means that if you remember the equation before, delta t equal A delta m, in this case, delta t equals 0, because we know the flatten, we know the gather already flat. So we don't need to correct for the delta t. So this is a different kind of tomography. It's a special case of the tomography. We have delta t equal at 0, but the only constraint we have are the map misties here. And using that, what I'm going to compute is a new velocity model, which then will not only flatten my gather, still flatten my gather, but also all the lines will be tied to each other. So this velocity model will be valuable after that when I do some interpretation in a 3D sense on my 2D volume. So this is just an example to start with. So this is my first pre-stack depth migration, and you can see two lines which are crossing, this one here and this one there. And I have also overlay a pre-stack gathers as well, because in our system we can have pre-stack information, post-stack information as well. And as you can see, the velocity model is too slow, because all the events are pointing toward the top. So this is not a good model. So I need to do a few iterations in order to have a better model which flattens my gathers. So now my gathers are flattened, so the velocity model for each of the lines are good for each of those lines. But the problem I'm facing now is that I have some misties on those horizons here. So that's why we did the 3D workflow as I was showing before in order to remove those misties. And this is basically after removing those misties, the gases are still flat, but we don't have misties as well. So we have achieved our goal. That's all good. And now what I'm going to do is the most important point, the demonstration, for you to have a feel of what it's like as well. This demonstration will be done, I think I mentioned that before, on the cloud, for you to have a feel as well how easy it is to interact with your data set while you're on the cloud. So I'm just going to open my window here, which I prepared just before. Okay, so what you're seeing here on the screen, this window is what we call a session manager, which are different tabs for the different workflow, different software within our suite. And here on the favorites, it's all the things I'm going to use today in order to build this tomography matrix and to resolve this tomography matrix. So this is the tool I was mentioning before, which is the 3D visualization tool called 3D Canvas. And you can see here, I'm just displaying 7 lines, 7 2D lines. And overlay on those 2D lines, I've got 3 different horizons, right? And these are the information I'm going to use in order to build my tomography in the 2D sense and in the 3D sense as well. So again, this was my first PrexStack depth migration. I'm going to show you as well the first velocity model which was used. I'm going to overlay it on this section. So I'm just going to click here on section, properties, and then straight away I can merge and display the velocity. So you can see here displaying my first velocity model on top of the first PrexStack depth migration. Okay, and if you remember correctly what I said at the beginning, the first PrexStack depth migration was not good enough because our gathers were not flat. And I'm going to show you that now. So my gathers, actually I have some already displayed here, but it was hidden behind my PrexStack depth migration. And as you can see, those gathers are not flat at all. They're pointing towards the top. So when it's pointing towards the top, it's meaning indeed that your velocity is too slow. So we need to build a new velocity model which will take into account this fact here. So to do that, if you remember my the first presentation I gave before, what we need to do is first of all to compute the structural attributes. So i.e. the dip and the azimuth, the dip and the continuity in order to know where I'm going to shoot my rays from. So to do that, as you can see, it will be very interactive. I'm just going to click Interpretation, Seismic Attributes, and in this case, it's 2D section. And I'm just going to press Shift here, and all the lines are selected. And straight away, I can then click to the attributes I want to compute. So in my case, I want the dip and the continuity for the 2D sense. And I can see that the different lines have been selected. So I'm just not going to press apply here because I'm not sure you don't have the time anyway for me to see apply or something. If I do it, it will be very quick, but I have too many things to show you. So I'm just going to show you the results straight away after I've done that a couple of days ago. So first of all, what we want to see is the dip. So the dip is here overlay with my seismic as well. And you can see that the information about the dip is between -10 degrees and +10 degrees, i.e. the geology here is quite flat, so there's not too many structure in this case. Obviously, you have some artifacts here at the end that was due to the basically the migration problem of the aperture. So without that into account, the dip is quite flat. It's between -10 and +10. So then what I'm going to show you as well is the continuity. So if you remember what I said before, the continuity is a really good tool to tell me from which event I want to shoot my rays from. So here I have overlaid my continuity with a seismic. What is red means it's bad, so I don't want to take that into account. What I want is those blue events here, because it follows very well my structure. And this is the right information I want to when I want indeed to build my tomography matrix. Okay, so what we've done so far, we have our first model, we have our dip and the continuity. What we need now is to store those information into this unique database called a pencil, as I was mentioning before. So to do that, I put that already in my favorites here, and I'm just going to click on 2D Create Pencil. And all our imaging and migration tools within GeoDepth, you will see the same little window here, the multi-2D line launcher for all of them in terms of the 2D. So i.e., I can play with just one line if I want, or all the lines in one go. So in this case, I'm just going to show you, for instance, all the lines in one go. So I just click here to select all the lines. I launch the application, and then I can see that my model will also be there, so i.e. all the different horizons. And then I will just click select the inputs, and straight away, you can see that all those information will be stored in my pencil, i.e. the velocity, the depth, the continuity, and the PSDM. If I had by mistake not the right information here, I could have selected all of them in one go as well. Okay, I'm not going to run it again because I've done it already. And I'm just going to show you actually what a pencil looks like, because we talked about the pencil, but what it is exactly. So the pencil files are basically those vertical functions, and these are some example of pencil. And what I'm showing you is just one attribute. That just, in this case, I think that's just, I need to check actually. I think, let me check what I'm displaying here, but I think that might be the maximum result move out, which is another attribute which can be displayed as well. You can have also different attributes already done in your pencil. Okay, so now we have that. The next step is to run our pre-stack auto picker. I.e. on your CRP gather, I want to follow the curves because it's not flat yet, right? So to do that, I'm going back to my favorites here to the pre-stack auto picker. And I'm not going to show you the same step as before. I'm just going to select one line here, so just one line. And therefore, I'm going to show you a new feature in paradigm 19, which is the parameter testing table, which means that, for instance, I can set different parameters in one go. So for instance, I'm selecting here the vertical window range when I looked for those information. Every 25 samples, let's say. And I could also select other parameters if I want, and so on and so forth. Therefore, I will have different tests in one go. I don't have to run every time a new test. No, all the tests will be run in one go and will be then able to display that on your 3D canvas later. So I'm just going to show you the results now. So I've done some tests on my pre-stack indeed. So if I just show you the pre-stack gathers, and now I'm going to show you 4 different tests which were run on basically on this line. So I've got this first one here. I don't know if you can see very well the screen, but this first one here, you can follow indeed some events, but I'm not happy with some information here. I think it doesn't do a good job in some case here. But this was just one example, one of the multiple tests I've done before. So I'm just going to show you another one. And I think this one is a better one for this information here, which I know will help me for a better velocity volume to be computed. So this is the kind of information I will then be using for all my lines, and then I have the new results in one go. So this, again, this was just a test done for one inline, or one line in this case, and then after that, you run the same parameters for all the lines in one go. Okay, so we have done a lot so far. What we have done, we have computed the attributes, the structural attributes, the dip and the azimuth, the dip and the continuity, stored in the pencils. We computed the pre-stack gathers as well, NMO. And then after that, what we're going to do, we're going to compute my tomography in order to have a new velocity model. So to do that, and now you're very familiar with the flow, I'll have the same multi-2D line launcher, basically, like in all those 2D workflow, all the same. And again, I can do just one line if I want, or all the lines in one go. So I'm going to do all the lines in one go here. I'm going to launch the application. And basically, there are obviously a few parameters. I will not go into too much details here, not to bore you as well with that. The most important parameters here are the ray tracing, so i.e. the opening angle from where I shoot my rays, and also the aperture. And also, obviously, the update. So i.e. the sensitivity factor, which means if I'm already confident in my first velocity model, this sensitivity factor should be left quite a small value. Otherwise, if I'm not confident in my first velocity model, I should increase this value. That means the velocity model will be much more different. Okay, so let's say I've run anyway this first pre-stack, this first tomography before, And actually, I run 2 iterations because the first iteration was not enough. So I run 2 iterations, and I'm just going to show you the result after 2 iterations. First of all, on my pre-stack gather, and then after that, I'm going to show you on the pre-stack depth migration. So this is after 2 iterations. Sorry, I'm just removing that. And you can see if I compare now with what I had before, it's much flattened, so I have achieved a better goal. And I can look at other, obviously, gather if I want on the same inline here. So it's a much better velocity volume. But this is good for this line. Does it mean that for all the lines, we'll have intersection correct? Let's have a look now. So I'm just going to show you those pre-stack depth migration after a couple of iterations. That's those one here. So basically, I'm just going to show you 2 different lines. And we're going to check indeed if we have some misties or not. I can see here that indeed in this area, I've got a bit of a mistie. So this is not yet a VC model which will be good for this line as well as this line. Because what we've done so far is just a 2D tomography. So what we need to do is the second step of what we were mentioning before. I need to go on the 3D sense in order to do some map mistie tomography. Okay, so I'm going to show you that now. So basically, what we need to do is to build, first of all, the horizon misties. So to do that, I'm going to open a second interactive window called the base map, which is used basically to look at different horizons as a map sense. And on those horizons, I'm going to display the peaks which we used, first of all, for the third iteration. So that would be this one, for instance. And then I'm going to see straight away the misties here. So I'm just going to select all those lines. I'm going to calculate, and I'm going to show the misties. So I'm just going to select the right one. Oops, parameters, calculate, show misties. Here we go. So now, if I display those misties on the screen, I don't know if you see very well, but here I have a value of around 192. So it's quite a huge value in terms of depth. So obviously, first of all, what we need to do is to compute a mass mistie from those peaks. And this is what I've computed earlier on. So I'm just going to show you that overlay with those mistie. And this is the information, the main information we're going to use in time-preserving tomography. This time-preserving tomography, again, we assume that the gathers are flat. It's just those information, those perturbations, that will help us to have a new VC model which will be used to a new pre-stack depth migration. And I'm just going to show you now the result after a couple of iterations indeed on the pre-stack depth migration. So that's now PSDM volume 4. And I can see for this horizon which were here, it's now better tied. So indeed, I have achieved the fact that not only my gathers are still flat, but also the lines are better tied as well. Right, thank you very much for your attention. That was about it for this workflow. So again, as you can see, just to summarize, it's really a mix of working 2D lines by 2D lines, but in one go, and also working in 3D sense, i.e. converting your 2D lines into 3D volume, and also displaying those mistie maps, and then doing a time-preserving tomography, in order to achieve not only the flatness of the gathers, but also to achieve the fact that you have ties which are linked to each other. So that's actually my last slide, which is just for you to remember. If you have to remember just something, that's it. The word workflow is just to show you that you have a VC model which can combine those two things. Thank you very much for your attention.